was awarded by Bangalore University in 1986. Professor Udaya Shankar started his career as a lecturer in physics at the PS Junior College, Bangalore during 1973. He worked as a lab assistant at NAL Bangalore during the period 1975 to 1977. He moved to the Raman Research Institute in 1977 as a senior scientific assistant. He was a scientist from 1986 to 1993 and an associate professor from 1993 to 2000. Professor Udaya Shankar was a resident scientist at the Mauritius Radio Telescope, University of Mauritius, from 1992 to 1996. He became a professor in 2000. Professor Uday was in charge for the radio astronomy laboratory from 2002 to 2007 and coordinator A&A group during 2008 to 2011. Professor Udaya Shankar was also a member of the Murchison Whitefield Array board since its inception in its present form, representing Raman Research Institute, and served as a vice chair during 2 half-year periods. He was also the deputy project manager for a brief period. His topic of interest in the last 2 decades is low frequency observations of a redshifted 21 centimeter line of neutral hydrogen from the gas surrounding the first star born in the universe. Presently, he is an advisory member to a team working on designing and developing precision receivers deployed on the ground, water and space-based antenna orbiting the moon to detect faint radio signals from the intergalactic medium surrounding the first luminous object born in this universe. He was a representative of India in the Scientific and Engineering Advisory Committee of Square Kilometer Array, an international mega project with headquarters in Manchester, and the 2 large radio telescopes consisting billions of dollars built in Australia and South Africa. Also, he has been assistant editor of the Journal of Astronomical Instrumentation published by World Scientific. He was also chairman, Giant Meter Wave Radio Telescope Time Allocation Committee, NCRA, Pune, a center of the Tata Institute of Fundamental Research, Mumbai, during 2021 to 24. He is a member of the International Astronomical Union, IAU, former president, Bangalore chapter of the Indian Physics Association, and former secretary of the Astronomical Society of India, and member of the Optical Society of India. He has guided several students in their work towards a PhD degree, MS, MTech, and also taught graduate level courses. He has published more than 75 research papers in reputed journals, and he enjoys reading novels, writing poetry, and has an interest in cinema. I would like to thank you for accepting our invitation and to be with us, sir. It is a great pleasure for me to have you in our department. So I request on the behalf of the Department of Physics as well as behalf of University of Mysore to give a lecture on From Starlight to Cosmos, Learning Quantum Physics Through Astronomy. Now stage is yours.
One second, sir. Just recording and that's not like
Oh, it's for recording. Oh, okay. Oh, only one. Such a shame. I have seen Mysore Palace so many times. I have seen your Jagan Mohan Palace, Chamandi Hills. Hey, come on. And even I have seen Mainari Hotel. Today he took me to some other nice place to eat. Life is meant for enjoyment, and even Raman Institute going and coming from there is fantastic. So please, ask your teacher. Let's go, sir. So, or you write a letter or ask Amoga. He will take you to. Have you seen? Has he taken you to Kavlo?
Some of them came to
Some of them, all of you should go. You can't. There are some of the best things that we scientists in India, I'm not talking about myself, I'm including all of you, I'm saying, we have built some of the world's best telescopes in this country. And if you don't go to those places and see, who else will see? And then he said, we are building the world's largest telescope in South Africa and Australia with its headquarters in Manchester. If I remember right, it's a huge amount of money, 125, some 1,000 crores or something like that has been given by the government of India for such a large project. And without you, what will those telescopes do? I was there as a Science and Engineering Advisory Committee member till last week, and now I'm retired. After that, who will do science with the telescope, which is supposed to be the world's largest radio telescopes being built in South Africa and Australia? And it depends on all these bright faces that I see here. And if you don't go to Raman Institute, I mean, study in Mysore University is a fantastic place. I mean, study here and go and visit them, learn much more from them, and when you are a student, and that's the best time to learn, So, and then you go on in your life. That will be very much interesting. And then here is another person, which is very, very true. Indeed, I would feel that an appreciation of the arts in a conscious, disciplined way might help one to do science better. Look at that. The combination of science and art is something fantastic. Has anyone looked at his book called Truth and Beauty? Sir, I've seen the quantum mechanics note that my teacher gave, sir. Oh my God. Where did you get it from? My previous year student, sir. How come? Yes, sir, quantum mechanics has not changed in the last 100 years, no, sir. So therefore, the notes also has not changed in the last 100 years. So therefore, in that sense, you must read. So he says he's not asking you to read anything about science. He's asking you to read about arts. So you see, just now Amoga took me to Jayalakshmi Palace, where the folklore, this thing is there. I was very keen to see D.V. Gundappa and B.G.L. Swami's artifacts being displayed there. But unfortunately it was closed, but they did show me lots of things. They want to do radiography on the art pieces there. Oh, fantastic place. Unfortunately, it is closed up to 2027, right? And that's what we saw. Otherwise, I encourage you first go there and enjoy, and then we can do lots of other things. Okay? Let's come back to the talk that I'm supposed to give you. See, radio telescopes, has anyone seen a radio telescope or read about it? Illa, sir. Howdo, sir. Okay, fine. So, the telescope in which I did my PhD thesis is 1 kilometer by half a kilometer. My God, look at the size of the telescope that we are talking about. And then the telescope that I and my students built in Mauritius is 2 kilometers by 1 kilometer. And the telescope in which he said I was the chairman of a time allocation committee in Pune is one of the world's largest radio telescope, is 30 kilometers. So look at that. And then the telescope that is being built in South Africa and Australia, the sizes go up to 70 kilometers, or even little more than that. I don't have slides of them. That's what I was telling him, that call me again, I will come and talk to you about not physics, but about telescopes, how telescopes work, and how come such a huge telescope, 30 kilometers, sir, how can a telescope 30 kilometers work, sir? There are lots of interesting questions, and believe me, they all depend on physics. Physics, that to what? You have all heard about Young's double slit experiment? Right, very good. So that's one of the fundamentals of quantum mechanics, right? That is the interference of light, and then you have also heard about interference of electron beams. Be brave, don't worry. Yes, sir. So, which is talking about the particle and the wave duality and other things. Well, that is the basis of quantum mechanics. That is the basis of learning quantum physics. That is, quantum physics means all about duality, right? It's not about reality, it's about duality, right? I mean, that's why, I am always a dual person. I sell myself to all physicists as an engineer, and if a physicist talks to me, I say, sorry, sir, I don't understand physics because I'm an engineer. And then if an engineer comes and tells me too much of engineering, I say, no, sir, I did my MSc physics, sir, I don't know engineering. So, therefore, to be an astronomer, you have to have the duality of engineering and physics both. If you don't know engineering, there is a problem. The scientist will sit on your head. If you don't know science, an engineer will sit on your head. So it's better to be, good converse with both the topics. It will be very useful. All right. So let's go to the next slide and start the talk. Otherwise, I promise that I will finish it as soon as possible. Well, I sometimes don't. So we will see. So, astronomy, this is a spiral galaxy, right? Beautiful pictures. Astronomy means beautiful pictures. Astronomy investigates the origins, structures, and dynamics of stars, planets, galaxies, and the cosmos itself. And if you ask today, what's the size of the cosmos? Does anyone know? Or the size of the universe? Okay, how far is the sun from you? We have come to listen, sir, not to answer your questions. Don't remember? Yeah, correct. How long the light will take from sun to reach you? 8 light minutes, that's all. Whether you say in Bangalore to Mysore is 2.5 hours, sir, it's all time. But it's also 150 kilometers or so. But either you can say time or you can say velocity. And the most beautiful thing about the entire physics is velocity of light is constant, right? So therefore you can say 8 light minutes. So similarly, imagine 8 light minutes. The size of the cosmos is 13.7 billion years. Right? So that is what the astronomy is about. The astronomy investigates origins, structures, dynamics of stars, planets, galaxies, and cosmos, which is 13.7 billion years. Maybe I have a slide in the end, I will show you. Whereas when you talk of quantum physics reveals the rules that govern the nature at smallest scales. Processes within atoms, nuclei, fundamental particles. But believe that it is these processes that power the stars and shape the cosmos. Beautiful combination, right? One is so small, but still it controls such a big structure. So that is the unification of concepts. From these two disciplines, we gain hopefully very good understanding of physics and not of engineering. Mobiles are not allowed, sir. The WhatsApp, you can wait. You are not married, right? Yeah, because married people have a problem. Where are you? The wife will always send you a question from wherever you are. If you aren't married, if you have a girlfriend, then I'm sorry. Then you have to answer your wife much more, a girlfriend much more than your wife, and it's a problem. So I apologize if anyone has your mobile on. I think I switched off, but I'm not sure. If it rings, if my wife asks, where are you? Then I may have to answer. Okay, all right, thank you. So by unifying concepts from these two disciplines, we gain profound insights into the fabric of reality, evolution of universe, and our place in it. So it's a beautiful combination of two topics, which I recently came across for some reason, and therefore I am here to talk to you about it. Well, there are two things which are happening today. Today means in an overall sense, today. One is 2025 marks 100 years since the revolutionary quantum breakthroughs of 1925, right? That is, this was the Annus Mirabilis, which is Latin for the miraculous year, when Heisenberg, Schrödinger, Born, Pauli, they published foundational works in quantum mechanics, 100 years, right back. And the UNO, led by UNESCO, proclaimed 2025 as the International Year of Quantum Mechanics. And we also know that the 19th century, if you really go back and look at it in an overall sense, it is known as the machine age. You have thought of so many machines came into existence in that 19th century. 20th, as the information age, which you saw our friend looking at the mobile, he can be contacting, talking, or thing, I'm not making fun of you, to really, talk to abroad. Many times I keep a walk and then I'll be talking to my daughter in US. My God, information age is fantastic. And that's what the information age, which was last century. And Paul Davies says the 21st century will be of the quantum age. Beautiful, right? What is quantum age? Okay, at least tell me, why should it be called quantum age? Anything that really have heard of, the newspaper, everywhere you keep hearing about it. Come on, go ahead, don't worry. Yeah. Quantum computing, at least, don't ask me what it is, don't worry, but quantum computing, at least let's know some words, if not the complete understanding of it. Quantum computing. So quantum computers are a thing. Well, it may catch up, and that may be the 21st century, may be the year of quantum age. So with that, quantum mechanics plays a very prominent role. So 2025, milestone, UN International Year of Quantum Mechanics, 2026, 101 years of quantum mechanics. Well, we are all here to celebrate that within 1 year late, so I said 101st year, why not? We'll call it that way. And then the next, here are the, gratitude is very important in life. Those two did not say, maybe. Well, so the gratitude for teachers who taught you, and what I am today is because of my teachers who taught me at various levels. So therefore, if you want to really look at quantum mechanics, all these names are familiar to you. Can I read them? Louder! Sorry, I am afraid of Dirac. Don't ask me. I don't understand Dirac at all. The rest, at least somewhat, I understand. And then here there are three people who contributed a lot to quantum mechanics, but as Professor Deshmukh, I took this slide from him when he spoke last time. I stole this from him. And then he showed three people from India who have contributed enormously to it, but whose names don't appear here. One is Meghanand Saha, then this is Raman, and this is Saha, Raman, and the other name must be? At least after hearing that, be good to copy both. Copying is the best form of flattery, right? I mean, if you copy, who is a famous actor, in a comic actor, you get Charlie Chaplin. Charlie Chaplin once competed to in a show to act like a Charlie Chaplin, and he won the second prize. So like that, it's very important. Copy is flattering, so don't worry. So those are the three people who contributed a lot. And today, the first slide I thought had that. I did not perhaps tell you about it. This is this is gone. Okay. So, I hope I have got. I don't have the latest one in this, or what? Which one did I see? It's there. Sorry. Thanks. So I put it up here. I thought otherwise this is not the last slide that I gave you. I don't know what else will be missing. So today is National Science Day, and National Science Day 2026, and so National Science Day is observed to mark the novel discovery of Raman effect by Raman in 1928. So Raman effect is a phenomenon in spectroscopy discovered by him while working in the laboratory in Indian Science Cultivation of Science in Calcutta, and he brought the first Nobel Prize in 1930. You've all heard of this, looked at it. But here the most important part of quantum mechanics comes, wherein I think I have it in the next slide. And then every year the theme of celebrations changes. And do you know what's this year's theme? Smile. I'm glad she's smiling. Women in science, right? I mean, so enormous amount. I don't know whether I could put this picture. I think I have it. Yeah. Look at that. These are my colleagues at the Raman Research Institute. Oh my God. There are engineers. Oh, I'm sorry. There are engineers, Vani and, oh my goodness, sorry. You've heard of Urvashi Sinha, who is a quantum mechanics person who did a lot of work on quantum physics and particularly quantum keying. Sangeeta Roy, even Sita she's an honorary member who works in the department of ISRO, but who is working at RRI now. Look at that. So I want your pictures to be there in a short while, and I mean, of course, they all should retire sometime. And then when they retire, that's time for your pictures to appear there, right? So that's what, I mean, today we are celebrating National Science Day to commemorate Raman's birthday, but to commemorate, in a sense, the word women in science and technology. And this is women in science and technology at RRI. I think you should all give a clapping hand to them, And I would like to give a clapping hand and welcome you to this side of the table as soon as possible. Okay, that's I think a very important thing to happen. Okay, let's not get into all these details, but we will just see the real inspiration of science is essentially the love of nature. That's what I just said, and that's what here he says. Ask the right questions and nature will open the doors. So question and nature are two very important things of life, and that's what Raman said. You should read this lecture, Why the Sky is Blue. Oh, beautiful. My God, he was an orator. I was very lucky that I heard one lecture of Raman. You know, when I was in first honors, he came and gave a talk on diffraction, and I was very happy to listen. And then, I was remembering Sir is saying, close your lecture at 1 o'clock. He spoke, and somebody, he said, he used to breathe, you know. How long am I supposed to speak? Said there was Professor Paramashwari, I was sitting in the front row. So he said, Sir, you were supposed to speak for 1 hour and it's over. He said, I stop here. That's it, he stopped it. Tarak. And then he asked wonderful questions, and that 1 hour was really fantastically exciting and very nice. I never dreamt that on this day I would work in Raman Research Institute, but I was lucky. I say many times to many people that I was very lucky that I got a position to work in Raman Institute and spent a lot of time with the director who also happened to be related to Raman, and it's a wonderful place to work with on science. Okay, so next go. So Raman also said you have to publish or perish. You see, he goes in a boat and finds out why is the color of the sky blue, and also the color of the sea is blue. And as a matter of fact, the color of the sea is blue sort of contradicts or does not agree with what Lord Rayleigh was saying in those days, but he did not bother. He said courage, conviction and confidence are important in science, and he publish or perish. He would really, if he finds something interesting and if he's confident of what he has done, he would publish it. So that's the other most important part of science that you have to do. You have to be courageous, conviction and confidence, and then you have to publish what you have done. If you don't show what you have done to the world, it's a waste. It's a waste of the government money. It's a waste of all the funds that we receive. And that's what we're seeing here. See, look at the beautiful picture of Raman Institute. It's so nice that I had an office room which was overlooking all this greenery. It's really, one has to be lucky. This is the library, one of the best libraries that I've seen. And this is now the Platinum Jubilee year of Raman Research Institute, 75 years since Raman started this place. This is the library. Yeah, so now let's come back to a little bit more of science. Otherwise, people will say, look, you came all the way, only said something about Raman and International Year and didn't go away. All right, so this is what I said. At sunrise, the world is washed in gold, and every shadow learns to dream again. It's from a poet unknown, and it's 8.3 light minutes or 150 million kilometers away from us. Suppose one measures the amount of the radiation coming from the sun in various wavelength regions from 250 nanometers to about 2500 nanometers. This is the curve that you would approximately see, the yellow one. These are all measurmental errors and things like that, right? And if somebody asks you, hey, which law does this follow? What would you say? Saying Wien's displacement law. Well, that is actually, I should ask the question in a slightly different way so that the answer fits perfectly. That is, well, come on, look at the sun is 8 light minutes away from us. 150 million kilometers. What the bloody heck? You are saying 5,778. If somebody asks, this is a standard question in all interviews. What's the temperature of the sun? Huh? I don't know. Perfect. Around 6,000. If you're a part of the student, I'd have said, please give her a clapping hand. So, I'm just keeping quiet. So sorry for saying that. So it's about 6,000 degrees. Did someone put a thermometer and measure? Then how do you know? Stephen Boltzmann law, then she already said one Wien's displacement law, that's more correct for that 6,000 degrees. I mean, then anything else? Just a little louder. Don't worry, this is not exam, I'm not going to give you a mark. Rayleigh-Jean's law, at least that's the one that I was looking for. Because why? Because people, the early days of classical physics, people tried to describe all these laws by using Rayleigh-Jean's law, which is 2 nu squared by kBt by c squared. That's the classical theory of light. And when you use that, there used to be something called an ultraviolet catastrophe. That is, if you use this Rayleigh-Jean's law to describe the sun spectrum that we obtain, then if you use this nu, as the nu goes to very higher frequencies or shorter wavelengths, then you will find that this expression shows nu, the B goes to infinity. That is what is known as ultraviolet catastrophe. That means even sun in those days, we were not able to exactly understand and fit a law to the sun's radiation. That was the state of classical mechanics in those days when the Rayleigh-Jean's law showed a UV catastrophe, and therefore we had a Planck who resolved this in 1900 by proposing that the oscillators in a black body do not emit energy continuously but in discrete packets. That was the starting point of louder. Yeah, I think you'll all get a clap for yourself in quantum mechanics. Beautiful. So that's the first picture we had, right? Planck at this corner was Planck. So that's how this began. So look at that. Simple. The sun is the nearest star. We are trying to have his a spectrum in this frequency range, which I showed you on the graph, and there the Planck's law could fit well. And Planck, what did he do? Planck simply used, here, Planck introduced the relationship E equal to h nu, not h by nu, sorry, there was this E equal to h nu, where h is the Planck's constant. Okay? So, why was this revolutionary? Because it was the first time energy was assumed to be quantized, not continuous. This successfully explained the observed black body spectrum, and it marked the birth of quantum theory. And what happened? The brightness temperature as a function of frequency of a black body is given by 2h nu cubed by c squared into 1 over e to the power of h nu by kt minus 1. Units? I didn't write the units purposely. I think I wrote it somewhere next thing. Physics, engineering, both needs proper units. Whenever you want to measure something, you want to connect it to what you have measured, what you know. If you don't know the units in which you have measured, it will be difficult. So, brightness temperature or the brightness distribution in the sky, B nu T. Do you know, anyone knows what that thing is? No, it's okay. Time is getting out, so let's go. Watts per meter squared per hertz per steradian. Don't write it down, but write down and go and ask what are the units of Planck's law. There are 2 different ways: per unit bandwidth, per unit wavelength, and then energy density and brightness temperature. There are so many different ways of expressing Planck's law. Each one, what are their units and how does the Planck law look like? Just go home and do. It's very easy these days. Go and pray. Which God do you pray? Huh? No. ChatGPT. Oh my God, she is advanced. I am still an old timer, you see. She is right. You should go to ChatGPT, but I always go to, somebody told me, go to Google and say, and then, do this, and the Google will bring the answer. But then somebody told me, a very nice a foreign scientist who came to NIAS, where I was working for a day or two, he told me, be careful. This Google God is like almost Hanuman. I said, Hanuman? What's Hanuman? Yeah, Hanuman. He brought all the plants on the Sanjeevani Parvata when the Lakshmana was unconscious, because he didn't know which plant to be used, but he knew that it is on the Sanjeevani Parvata. So similarly, Google gives you an enormous number of answers, and then you don't know where it is. And then ChatGPT, she's right, use ChatGPT today. I completely agree with her. But then remember, always ChatGPT says, look, the ChatGPT could be wrong, right? I mean, it always says. And then I was doing some work on a poetry. How many of you have heard of D.V. Gundappa? Oh, very good. Oh, thank you. I think I should give you a clapping hand. So I was trying to do some analysis of Mankuti Manakagga, and ChatGPT worked very well. And then it did not have in the public domain all his poems. So it said something. I said, sorry, this is not the real original poem thing. I cannot be in this fashion at all. This is the meter that Gundappa uses. Sorry, you have given me a wrong poem. He said, I'm sorry. He just tried. If this guy accepts, it's okay. But you have to be very careful. So if you're not careful, it can misguide you. So be careful. ChatGPT or Google. All right, fine. So you can get all the answers to that. Let's go to the next slide. So today we know the sun's radiation is a good approximation of black body radiation with wavelengths in this range 200 to 2600 nanometers. And that's the first picture in the series is Planck. That's what Max Planck was initially skeptical of his own quantum hypothesis. He didn't believe it himself. It contradicted classical physics, which he deeply trusted. See? He viewed energy quantization as a mathematical experiment rather than a fundamental truth. Look at that, even the greats have problems, right? But it's good to know them. That's why I'm just stating them. He explicitly stated that he did not believe oscillators truly emitted energy discontinuously. That's the basic of quantum mechanics today, but he didn't believe. He delayed fully embracing quanta until Einstein in 1905 explained the photoelectric, explaining the light as photons, and then of course Einstein went on to win the Nobel Prize, and Einstein got Nobel Prize not for relativity, either special or the other relativity, whereas he got it for photoelectric effect. That's another point. That's okay, doesn't matter. So that's the first story of the first Planck and the sun as a star, how it emits as a black body, and how the classical physics failed and the quantum physics brought life to black body radiation, understanding that. Why stars shine? That's the next quantum story. What is that? When you look up at the night sky and see a star twinkling, you are actually seeing light that begins journey thousands of years before. But here is the mystery. What makes that light? Especially its spectrum. I'm talking about spectrum because when I want to introduce quantum mechanics, spectrum is more useful to talk about. The answer takes us to one of the most beautiful ideas of quantum physics, and that is, imagine every star, including our sun, as a huge collection of atoms, mostly hydrogen. Hydrogen is the most abundant element in the universe. Inside each atom, there are electrons moving around the nucleus in certain orbits or energy levels, and these electrons cannot move freely anywhere they like. They can only exist in fixed energy steps. This was one of the first quantum discoveries. Energy is not continuous, same as E equal to h nu, but slightly in a different context, but comes in small packets called quanta. Who was the man who started this? What's his full name? Niels Bohr. You're getting tired. I told you by the end of my talk you'll all be hungry. Luckily there's no door there, right? Is there a door there? Oh man, I should go and lock that door before I start. Otherwise I'll be lecturing only to half the class. That's all right, fine. So Bohr was told by one of his friends that Balmer series is an empirical equation discovered by Balmer in 1885 that describes the observed spectrum of stars in terms of spectral lines of hydrogen. See, Balmer series is well known, right? Yes? Good, at least somebody nods their head. I feel happy, I don't feel sleepy. Okay, this was further generalized by Rydberg, and we have the Rydberg's constant and all his equations we have. So let's go on. So Bohr's key postulate is that the electron in the hydrogen atom can move only in orbits for which its angular momentum is integral multiples of mvr. So that integral multiples of mvr, that's the basis, once again, that Bohr brought in. He explains that this selects a discrete set of radii and energies. and the quantum emits or absorbs light only when the electron jumps between these quantized orbits with photon energy given by the difference of these orbital energies. It becomes clear to hear more that each orbit has a constant radius directly related to energy. These energy levels are characterized by, oh, I don't get that fine, no problem, our principal quantum number, and larger the radius, higher the energy. N equal to 2 has greater energy than N equal to 1, and the electron in the ground state is N equal to 1, the principal quantum number. And then the important thing is we are talking about is that when the electron transits from principal quantum number N equal to 3 to 2, you have a spectrum in red, and when it goes from 4 to 2, you have it in green, and when we have it in 5 to 2, you have a violet line. Beautiful. And then there was this, the axial observed hydrogen bomber absorption lines in a star spectrum. This is a real star spectrum. A star of a type A. Have you heard of this? B, A, F, G. Some heads are saying there, half the heads are, my problem used to be when people, there used to be a small class of 10 for the solid state. So what happens, sometimes we would do this, and then Professor Kuchela used to be the teacher. He would say, what is this? It has to be either horizontal or vertical. What is this 45 degrees? He would say, so not like 45 degrees, that's all right. So here are the true lines of Bowman lines seen in stars. And they exactly fell at the lines predicted by Bohr atom. So that's the other nice thing. You have a spectrum and you have Bohr's theory of atoms, and then they started matching. But of course, before that, Balmer himself had given an expression, but it was empirical, whereas Bohr made it more clearer, and that's the next step of the quantum mechanics that we came across. Apply to stellar spectrum, and there, bingo, we were there. But here is something more amazing. What is amazing? Each kind of atom gives on its own special curves of light, its own fingerprint. Just today morning, somebody sent me a very beautiful poster saying that when we got educated, we moved away from thumb impression to our signatures, but with technology, we have gone back to a fingerprint. So, like that, each kind of atom, its own special colors of light, it's called the quantum fingerprint. And when astronomers pass starlight through a prism or a spectroscope, they see a rainbow-like pattern with bright and dark lines. The lines tell us exactly what the star is made up of. Beautiful. So, without putting a thermometer, we know its temperature. And now, without going there, we know what it contains. Beautiful. Right? So, next, how the sun revealed helium in India. Helium was not an atom well known before 1868. It was total solar eclipse, and scientists or astronomers from England and France had come to a place called Guntur, very close to Andhra Pradesh, very close to Bangalore, and they saw in the chromosphere of sun, when there was a total solar eclipse, two lines of atom which was not seen on the earth. And because it came from the sun, they called it as a helium, which means they saw, let me just read, in the yellow region of the spectrum, they saw a new bright line close to the sodium D line, but slightly different. The line did not match any element on the earth. And we have the discovery, and that's the discovery of the helium. I don't want to take more time, but let's go back. So from the light of the sun during Indian eclipse, humanity discovered a new element called helium, written in the quantum colors of starlight. Wow, beautiful, right? So romantic that you have sun, we have quantum mechanics, we have India, we have spectra, we have astronomy, all combined together to give a new element, helium, right? So nice to see. Science is exciting. Particularly, I will show you, but unfortunately, we all think science class, ಕನ್ನಡ ಅಯ್ಯೋ ಕನ್ನಡ ಯಾಕೆ ಓದ್ಬೇಕಮ್ಮ ಕನ್ನಡ ಇಲ್ಲಿ ಏನು ಪ್ರಯೋಜನ ಇಲ್ಲ ನಮಗೆ ಕನ್ನಡದಿಂದ ಬೇಡ ಸೊ ಕನ್ನಡ ಬೇಡ ಸೈನ್ಸ್ ಬೇಡ ಇಂಗ್ಲಿಷ್ ಬೇಡ ಏನ್ ಬೇಕು ಬರೀ ಸಾಫ್ಟ್ವೇರ್ ಬೇಕು ಸರ್ ಸಂಬಳ ಬರುತ್ತೆ ಸರ್ ಐ ಕ್ಯಾನ್ ಗೋ ಟು US it's not true. Science is exciting, enormous amount of excitement. Look at all these guys, all these pictures you have. I mean, they would have, seeing them every day itself is enough, and working with some of them was itself as fantastic to me. I mean, I have seen him, I heard so many lectures from him. He used to come to Raman Institute a lot. All right, fine. Boy, anything in science is not stationary. It keeps on changing, right? So there was limitations of Bohr's atom. So what is the most important limitation? It works for only hydrogen, helium and lithium, but fails for multi-electron atoms. It assumes definite orbits contradicting quantum mechanics where this cannot be known precisely. Heisenberg's uncertainty principle is slowly coming up. It cannot explain fine structure like Zeeman effect and Stark effect. And it does not incorporate wave nature of electrons or explain the shapes of orbitals and offers no explanation of how atoms form molecules or chemical bonds. You are so happy. Bohr, fantastic. And limitations of Bohr. Next is the limitation. That's how science progresses. That's why you ask more questions, then the nature opens up. So what are the questions? These limitations led to the development of modern quantum mechanics. One step further, which uses wave functions, wave and a particle. You have wave-particle duality, which I spoke about in the beginning, and we started talking about probability in quantum theory. But sometimes I don't know where it goes. Yeah, probability in quantum theory. So in moving from the original Bohr model, we completely abandon the idea of orbits. What do you mean by that? Let's see whether I can make you understand. Very simple experiment. Suppose, thought experiments are very useful. If you go to your teacher and you start, let's see how I learned most of my astronomy through most of astronomy experiments that I did in a lab at RRI or in the field. My professor Radhakrishnan, who was the director of Raman Institute, would say, yeah, what did you do? Okay, let's see what you did and how it would, then both of us after 10 minutes we would know what mistakes we were doing. So all these discussions were about mistakes. So what is the mistake in Bohr atom? So next we suppose we prepare a sample of hydrogen atoms in a ground state. Really sir, not possible. Yeah, don't worry. It's a thought experiment, right? We said it's a thought experiment. Next, we make a series of measurements to determine the distance of the electron from the nucleus for particular atoms. If you measure where the electron is from the nucleus, then you will find we do not find a single well-defined distance. We do not find a single well-defined distance. The Bohr theory predicts the orbit to be 0.53 angstroms, but instead we find a range of values. We find a range of values, and the most probable result is 0.53, but there is an appreciable probability for finding both larger and smaller numbers. That's why we have here this graph. Sorry. Yeah, that's no, not this. You right. So this is the thing that you find here. You draw the probability, or probability is nothing but you conduct 1,000 experiments. In 100 experiments, it will be at 0.53. In another 25 experiments, it will be at 1. Another one, it will be at 0.25. And that's what you draw. The number of times you found that in a given experiment, then you get a probability distribution. And that's what this is. So it won't be there. That means the electron does not have a particular orbit, and whenever we measure we don't get that value 0.53, but there is a probability distribution of the electrons. So that is what the whole thing is. So this starts with, if it was a particle like that, it would have been in a given orbit. And there the next aspect of the quantum mechanics came in when we said wave-particle duality of light. Max Planck's work on black body and Albert Einstein's explanation of photoelectric effect established that light, traditionally viewed as a wave, also has particle properties with energy E equal to h nu. Thanks that my slash has gone, which I wrote h by nu in the earlier slide. I'm sorry for that mistake. It was a typographical error. So it's E equal to h nu is correct now. Right? So we have the light, and therefore the next important step in the quantum mechanics came when de Broglie hypothesis. He said that if you have a particle, its wavelength can be thought of as equal to Planck's constant by momentum. You know momentum, right? And therefore you know the Planck's constant by Planck, whatever, and then you can say that a particle is associated with a wave whose wavelength is Planck's constant by momentum. That's the de Broglie wavelength. So beautiful. So we go in steps from left to right. If you remember the slide I showed, close your eyes, don't sleep. You have Planck, then Bohr, then de Broglie, and then next is Schrodinger. Sir, 12:59. Shall we stop after?
No, for another. How much time?
Okay, fine. Thank you. All right. Yeah. So Schrodinger equation was developed to provide a mathematical framework for the wave-particle duality. I didn't want to go into equations, so I have not written much of equations. So just like the Newton's laws could explain you how a particle travels with time, that is, you have space and you have time and you have Newton's laws, you can look at time and space. Similarly, how does the probability distribution psi moves with space and time was given by the Schrodinger equation. See, we all write Schrodinger equation. That is quite, I think I've written it to the next slide. I'll show you. But we don't know what psi is. We forget it. So try to connect it with a little bit of physical understanding. You will enjoy it. So that's what the Schrodinger said. Erwin Schrodinger was primarily motivated by classical mechanics could not explain this, and therefore he wrote down an expression. Let's jump. The Schrodinger equation emerged from early 20th century of atomic puzzles. Schrodinger derived it in 1926, and it's like Newton's second law, and this is the Schrodinger equation. I will not like to go into great detail, but this, you have done Schrodinger equation in the class, right? And then you have derived it to psi in energy levels of a particle in a box. See, I did in 1973. I still remember. Particle in a box. And then what is the next one? Hydrogen atom. You derive it for the hydrogen atom? See, thank you. Harmonic oscillator. That's the most important thing. Harmonic oscillator is very important because when I learned my quantum mechanics, the most exciting thing that I learned is harmonic oscillator. Hey, there is nothing like a harmonic oscillator. Everything is anharmonic. So if you take an atom in a substance, it's not a harmonic oscillator, it's anharmonic. The potential is not symmetrical. That's why you have expansion of solids. It's anharmonic. Therefore, you can always view the anharmonicity as a small perturbation in harmonicity and derive perturbation theory. Right? So beautiful. So this is how one of the teachers taught us quantum mechanics when I spent a month in BARC in Mumbai. And he was Professor Balkrishnan from IIT Chennai, who writes the introduction to Feynman lecture series. Have you looked at the book, Feynman lecture series? How many of you have touched it? Oh, beautiful, good. That's good. I have touched it, So thank you. So go read. Don't worry. Sometimes, take them. There will be a little bit of dust on them because not everybody reads it. So put them off and then look at it. It will be exciting. That's it. Very exciting books. He taught physics very beautifully. And there are so many YouTube. Don't worry about going to the library. I mean, somebody will scold me if I say this. There are so many friends of mine who would take me, cinema, YouTube, they'll say. So, therefore, but I say, go to the YouTube. Ask, what did Feynman say? Can you show me a YouTube? There are so many videos today on Feynman. Some of them are made using artificial intelligence. Be careful. But otherwise, there are beautiful lectures by Feynman you can find on the YouTube. Enjoy it for 10 minutes, 15 minutes, then go to sleep. It's all right. So, okay, fine. So, So the Schrodinger equation is, it grounds how the wave function describing probability amplitudes evolves over time given the potential V. It does not give exact paths but distribution of psi square. Sir, you're going into quantum mechanics, sir. We have already read so much, sir. You said star. Where is the... wait. Yes. The next thing, after Schrodinger equation, it is star. Actually, when I read this recently again, I myself got, oh my God, oh, this is how the star works? I was a bit doubtful. I said, my God, I've forgotten this. I didn't remember it in my classwork of 1973. So I called one of my students. I was very lucky, as I said, I had very good, bright teachers. I had very good students also. I said, hey, Saurabh, do you remember this? Of course, sir. This was taught to me in the class. Oh, I said, okay, fine. Beautiful. Because Hans Bethe established that sun-like stars shine by converting hydrogen to helium through proton-proton chain, for which he won the Nobel Prize in Physics. You all know proton-proton chain? Some heads are doing this, the other heads are very stationary, stable. This way or this way. Yeah, so proton-proton chain gives a lot of energy. The proton-proton is called, fusion. It's called fusion. What has got fusion to do with Schrodinger equation? Well, that's where the beauty is. The sun, like a star, its core temperature is 15 million degree Kelvin, giving protons only 1 keV of kinetic energy. You can equate, na? E is equal to h nu is equal to kT. You can get all those things and get the equivalent of energy, right? Far below the 500 keV required for overcome the electrostatic repulsion between positive charges, two hydrogen atoms or two protons. The two protons repel each other. So when they repel each other, when they have to fuse, they have to overcome the force of repulsion and get fused, right? But where is the energy? The temperature is only 15 million Kelvin and it's not enough. Where does this energy come from? Classically, the protons must collide with enough speed to overcome repulsion and let the strong nuclear forces bind them at 1 femtometer distances. At stellar densities and temperatures, direct classical, at stellar densities and temperatures, direct classical overcoming is exponentially rare and stars would not ignite at all. There will be sun without light, right? It won't be a star, which is the most well-known object which could have been a star but which is not. Jupiter. Say, Jupiter, it is almost on being a star, but somewhere it's left out of it, and it is no more. It's not a star, not no more. It's not a star. So star throws its own light. So what's happening is at stellar densities and temperature. Then how, sir, you are saying all these things? Then where? How can it work? That is the answer. Quantum tunneling. And quantum tunneling comes from Schrodinger equation. When you write, because the time is getting out, so I will just take this. When you have a potential well, if according to classical physics, if there is a particle which is in this bottom of this potential well, it requires an energy greater than this to be available here. Whereas quantum mechanical tunneling tells you that if you have a Schrodinger equation and write down the psi, then you will always find a finite probability of finding the electron on this side also. Beautiful. So the quantum mechanical tunneling is a phenomena where the particle passes through a potential energy barrier even if it does not have enough energy to classically to overcome it, due to its wave-like nature. And the probabilistic rules of quantum mechanics allows a non-zero chance for the particle to appear on the other side. That's what the Schrodinger equation is, and therefore Coulomb barrier prevents classical fusion at stellar temperatures, but quantum mechanical tunneling allows wave functions to penetrate barriers, and protons fuse despite insufficient kinetic energy. Wow, beautiful, right? And high density ensures frequent tunneling events over billions of years. And we have sun ignited as a star. Beautiful, right? Okay, so that's after nuclear burning ends. How does the star live? Because you have nuclear burning, the sun is giving out energy, which is light, and then it also helps in the gravity, in acting against the gravity, and all this hydrogen has been burned out. How does a star like a white dwarf, here is the man who wrote about this white dwarf, who said it is the quantum electron degeneracy pressure which helps stars which have completely exhausted its nuclear fuel of hydrogen holds against the gravity. What is this electron degeneracy pressure, sir? Too complex, sir. It's becoming, we will go. Very simple. You ever heard of Pauli's exclusion principle? Right? Yes or no? Yes, sir. Pauli's exclusion principle, that is no two electrons can occupy the same quantum space. So, do you know what are the principal quantum numbers of, what are the quantum numbers of an electron in an atom? Loud, this you can't say, no, I don't know. Principal quantum number n, then spin quantum number. So, two electrons cannot have the same spin on all the other things in it. If you pressurize them, try to bring, they say, no, please move away. So they push each other. That means they provide force against gravity. And it is this force against gravity that Professor Chandrasekhar calculated and showed that this is very important. The Pauli's exclusion principle I've already told you. So that is the degeneracy pressure. The official citation from the Nobel Committee recognized his foundational work on stellar structure, particularly his discovery of Chandrasekhar limit. This limit was calculated when he was just 19 years old, and it is established when the maximum the star is about 1.4 solar masses. What he's saying is in this slide, what made him win the Nobel Prize also is that you push it, then yes, you can hold gravity. But if the star is greater in mass than 1.4 solar masses, then the way in which the electrons are pushed, it acquires velocities which are relativistic, and it cannot therefore start holding on if the mass exceeds. And then it becomes a neutron star, then a pulsar, and then you go to any lecture, it will be a black hole. So I think, friends, it's time. So let us stop at Pauli's exclusion principle. You have many other things to learn. Electron degeneracy pressure, I've said already, and more than that, I want to say, the entire universe is not all visible. The universe is invisible. What is invisible light rays? Electromagnetic spectrum consists of radio, light, there is the visible light, infrared, ultraviolet, X-rays, gamma rays. It was in the early time when Galileo looked at the night sky and then gave you all the fascinating things about the phases of Venus, the Saturn's rings, and the Jupiter's moons. That was only optical astronomy. But today, astronomy is multi-wavelength. You name any wavelength, we have telescopes. We have radio astronomy, we have radio telescopes. We have ultraviolet astronomy, we have UV telescopes. X-ray, we have a Chandra X-ray telescope named after him. So you have multi-wavelength astronomy. So what is the quantum mechanics in multi-wavelength astronomy, and what does it tells you? How does it work? Next time, next lecture, some other time, some other story, all in not in one movie. We always have KGF part 1, KGF part 2, so like that, Dhurandhar part 1, Dhurandhar part 2. So we will have Uday part 1, Uday part 2. See you. Thank you very much for listening to me.
Thank you very much, sir, for your illustrating connecting astronomy with quantum physics. So now the lecture will open for a couple of questions. If any students want to ask, Udaya sir, other than physics also it is fine.
Whatever you know, and whatever I don't know, I can easily say it's not in the syllabus. Yeah, please.
You said electrons for fusion principle cannot have the same spin quantum number.
Yeah, not only the same. I said of all the 3-4 quantum numbers, and all the quantum numbers cannot be same.
Yeah, but
Yeah.
even if it becomes any different cases.
Because two electrons can have the same spin if they have the different quantum numbers. They are not same principal quantum number, same orbital and other things. Yeah.
Based on that, you said they cannot hold. They can hold the gravity and water.
Yeah. It will take you into mathematics. We can discuss it offline. That is exactly the mathematics this gentleman did to show how the Pauli's exclusion principle, which is equivalent of not letting electrons come closer and pushing away, compensates gravity. So just a question of set of equations. We can write it down and see, or I can write it down and send it to you. No problem. It's pure simple mathematics. I didn't write equations. I wanted to keep them away. That's why I didn't write. But it's important to know that beyond 1.4 solar masses, I'm not saying what you asked is not important. What I mean is just for a hand-waving argument that when it goes beyond 1.4 solar masses, electron degeneracy cannot work. You need neutron degeneracy. And then it becomes a neutron star. Yeah, sorry. Yeah.
Did it go beyond X-ray astronomy?
Gamma rays. After the gravitational wave. So, beyond that, I don't think there is electromagnetic waves that exist. Is there anything beyond gamma rays? No, I don't think so. Correct. No, correct. Thank you. Yeah. So he's talking, said there will be high energy cosmic rays, right? Which could be more stronger than, more energetic than the gamma rays. Oh, there are Serenco radiation telescopes in Ooty. Go to anywhere, even if you go to honeymoon in Ooty, there is a beautiful telescope to see. Sir, who will go to a telescope, sir? What, sir? Doesn't matter, Yeah, it's a... No questions?
Any more questions?
Paravela, who is the hero of which movie also you can ask. I'll pass. Yeah, you have a question? Because I'll kele and the Yeah, fair. Big Bang Theory, okay. Parallel ಕೇಳಿ ನಂಗೆ ಗೊತ್ತಿದ್ರೆ ಹೇಳ್ತೀನಿ ಇಲ್ಲ ಔಟ್ ಆಫ್ ಸಿಲೆಬಸ್ ಅಂತ.
Before Big Bang, Big Bang theory ನಲ್ಲಿ ಏನು ಹೇಳ್ತಾರೆ ಅಂದ್ರೆ ಯೂನಿವರ್ಸ್ ಇದೆ ಫೈನೈಟ್ ಅಬ್ಸರ್ವಬಲ್ ಯೂನಿವರ್ಸ್ ಅಂತ ಹೇಳ್ತಾರೆ. But if we say it is an infinite universe, there are infinite number of stars. So in infinite number of stars is there. So infinite brightness, infinite amount of energy they will ಇದು ಮಾಡುತ್ತೆ, ಎಕ್ಸಿಸ್ಟ್ ಮಾಡುತ್ತೆ, ಅದರಿಂದ ಹೊರಗಡೆ ಬರುತ್ತೆ. ಸೊ ಇನ್ಫಿನೈಟ್ ಎನರ್ಜಿ ಬಂದಾಗ ಇನ್ಫಿನೈಟ್ ಲೈಟ್ ಅನ್ನೋದು, ಇನ್ಫಿನೈಟ್ ಬ್ರೈಟ್ನೆಸ್ ಅನ್ನೋದು ಬರುತ್ತೆ. ಬಟ್ ವಾಟ್ ವಿ ಸಿ ಇನ್ ದ space, it's like
beautiful. That is called Olbers paradox. It's very beautiful question. Thank you very much. Give my clapping hand. Well, I am afraid that in the next 5 or 10 minutes I may not be able to explain all that Olbers paradox very nicely. He says, look, all the stars, there are more, and then if you keep going away, the area, the surface area also increases, right? And therefore the number of stars you will see should also increase. And therefore if you plot log and log s, or how many stars that you can see as you keep going away, you are seeing more and more stars. It's only sunlight is required to illuminate the earth. Why do we see the night sky as dark? That is called Olbers paradox. I would prefer, rather than getting into details of it, just go and ask the Google God, read it, come back. When we come to KGF 2, I will start with Olbers paradox and Zeno's paradox, and then we'll go on to it. I promise you, I'll start my talk with that. Yeah, sure.
When a star, if it has more than 1.4 solar masses, okay, after it dies, it goes over electron degeneration.
No, not that way. It's the star with which it began. Like when you start about, I had them in my slide. It's okay. It's a very good question. Simple again, but nice. Here. So this is a mind sequence star. If it is already a massive star, then this is what it goes, and it goes through neutron star and a black hole here. If it is an average star like Sun, it becomes a red giant, a planetary nebula, white dwarf and black dwarf. This is the 1.4 solar mass we are talking about, roughly. And of course I agree that after it, this is the white dwarf is 1.4 solar masses. There could be a small variations and deviations here where it starts from. That's your question, right?
If it goes into
It goes into a neutron star. Yeah.
so that you mentioned about neutrons degenerate.
Yeah.
Then what happens if it goes to magnetron and what happens?
Oh my God, out of syllabus. Yeah, we can talk outside and talk about. See, magnetars and pulsars that you are talking about is a neutron star. A rotating neutron star is a pulsar, right? That's what we are talking about. And a magnetar is a kind of a different beast of all those things, of this kind of thing. So it's really what comes beyond this. It's very important questions, definitely important questions. Yeah.
So that is the interest on studying black holes.
No, neutron star study itself is huge, as a matter of fact. The studying of black holes, Kerr black hole, does black hole emit, can you image a black hole, event horizon telescope, that is another thing. So you have 3 points here. You have a white dwarf, you have a neutron star and a black hole. Sorry, this is a neutron star and there is a black hole. So all of them are very interesting thing on their own to study. Yeah, sure.
You mentioned about the gravitational waves. Could it be studied in supernovae?
What I know is, have you heard of IPTA, Indian Pulsar Timing Array? You haven't. Okay, fine. You can. Okay, fine. Sorry. They look at the pulsars and they look at the timing residuals of pulsars and try to understand as that evolution itself takes place, or if there is a binary pulsar and they are going around, what is the time residue that you expect and what you get. They fit it to a gravitational wave background of certain wavelength,
I have heard about the contact and collision.
Yeah, that is one which gives you directly the gravitational wave which we study. I'm talking about, it's not gravitational wave collapse, which gives gravitational waves of certain frequencies, right? Whereas what I'm talking about right now to you is the pulsar, study of pulsars, what kind of gravitational waves it lets you to understand. They're of a different regime. Just like we were talking about visible magnetic spectrum, electromagnetic spectrum, we have visible light, we have gamma rays, we're going radios and gamma at the 2 extremes, and you have different properties coming through. Similarly, the gravitational waves also, we have hertz, microhertz and things like that, and you will see different regimes under different circumstances in the universe.
Okay, if there are no questions, so I think we can wind up today's special lecture. Sir, I would like to thank you for 2 reasons. One reason is, for making our students smile. Generally, all our students, MSc students, their faces are like, looking at a horrible movie. But I'm thankful because, we made everybody at least smile today. So this special talk was...
Says no, we understood something, you say no in defense of me. At least you will see Durandar part 2, right?
I would like to thank you on behalf of...
thank you very much. Yeah.
As well as behalf of University of Mysore.
Thank you.
Now I request Hamurga Mosha to give vote of thanks.
On behalf of the Indian Institute of Astronomy and its field station COSMOS-Mysuru, I thank Professor Udaya Shankar for agreeing to come over here and give this lecture. Thank you very much, sir.
Thank you.
We were talking for some 2 weeks for this program and yes, agreed for this lecture. Thank you very much. And I thank the Department of Studies and Service and chairperson Professor Nyanka for his cooperation to for conducting this lecture and also organizing this. And we have full hall occupied. And thanks to all of you coming over here. And hopefully we'll upload this lecture and will be given a link to watch it later. And thank you, thanks for coming. And we'll be conducting more similar talks, workshops in the future with cooperation from Sir and the staff. Thank you.
So you always